This video will go through two examples of using the work-kinetic energy theorem to relate the force and the displacement of an object to its initial or final velocities. In our first problem here, talented barista is sliding a mug full of hot chocolate down a counter to an awaiting customer. We're given the coefficient of friction, and we want to know how fast did the barista push the mug. Again, we're assuming that it stops on its own when it reaches the customer. So we know that we're going to work with work-kinetic energy theorem because I told you that we were. And so that means that the net work on our coffee mug is equal to the change in kinetic energy. We're going to focus on the left-hand side of this equation first. We talked about how we can calculate the net work using two different methods, either by doing net force times displacement times cosine theta, or by adding up the work of each of the individual forces on the coffee mug. I'm going to use that second method. If I were drawing a free body diagram for my coffee mug, I would have the gravitational force acting downward, I would have the normal force acting upward, and I would have friction. I'm going to assume the mug slides to the right, so the displacement looks like that. And if that's the case, friction would be to the left. And it's kinetic friction because it's moving. So to find the net work, I'd be doing the work done by the normal force plus the work done by the gravitational force plus the work done by friction. That's equal to the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. So, then we have to figure out the work done by each of these forces. The work done by the normal force is equal to the normal force times the displacement times the cosine of the angle between the normal force and the displacement. In this particular occasion, because my displacement is to the right and my normal force is up, theta is equal to 90 degrees, and so the work done by the normal force is 0. Then we look at the work done by the gravitational force, which is the force of gravity times the displacement times the cosine of theta, or the angle between the gravitational force and the displacement, which is once again 90 degrees. So the work done by the gravitational force is 0. So the only work we really need to calculate is the work done by the force of friction, which is equal to the force of kinetic friction times the displacement times the cosine of the angle between the two. We know that the force of friction can be calculated by doing the coefficient of friction times the normal force times the displacement times cosine theta, coming from that work equation. In this occasion, my coffee mug is not going to rise up off the counter or sink down into the counter, and therefore the normal force is equal to the gravitational force. So I could write this work equation as coefficient times gravitational force times delta x cosine theta. Well, we also know that the gravitational force is equal to m times g, the gravitational acceleration, times delta x cosine theta. Okay. Now we can start plugging some numbers in. I know my coefficient, I know g, I know delta x, and I can figure out theta. The one thing that we're not given in this problem is m, the mass of my coffee mug. Now, just as we've seen before, when you're not given a quantity, it usually means that you don't end up needing it. So the way that I'm going to handle that is I'm going to plug in all the other numbers and multiply them by each other, but I'm going to just leave m in there as a variable. So here's what I mean by that. The coefficient is 0.42. I'll leave m in there as a variable. There's no vector symbol on top of my g, so I just plug in a positive 9.8 meters per second squared times my displacement of 1.7 meters. And I'm running out of room here, so I'm just going to write this below, times the cosine of the angle between the two. Well, you can see that my displacement vector is to the right, my force vector is to the left, so the angle between them is 180. The number that I get for the work done by friction is basically negative 7.0 times m. It's 6.997, so it's good enough to round that to 7. Now, pay attention that m is not a unit, that m is the variable. Be careful with that. It might even help us to put those in parentheses and then put the units that we know for work, which is joules, at the end here. Okay, so we now have dealt with the left-hand side of our equation, so we now need to deal with this right-hand side. We know that kinetic energy is equal to 1/2 mv squared. So if I'm dealing with the final kinetic energy, it's 1/2 mv final squared. If I'm dealing with the initial kinetic energy, it would just be v initial. Now, the problem told us that the coffee mug stops at the customer. So that means v final is 0. So that means this whole thing is equal to 0. And so that is equal to 0. So in my equation up top here, I'll mark that off. So now I can relate the work done by friction to 0 minus the initial kinetic energy, which is 1/2 m v initial squared. So let's plug in. We know that this is negative 7m equals negative 1/2 m v initial squared. Oh, luckily we see that there's an m on both sides. So if I divide both sides by m, that cancels out. So now I'm left with, and I can also actually multiply by negative 1 on both sides. So to solve for v initial, I'll multiply both sides by 2. So I get 14 is equal to v initial squared, and then I take the square root of both sides. I end up finding that that initial speed of the coffee mug is 3.7 meters per second. And that's a fairly reasonable speed to push something down a counter. Okay, let's try one more. In this problem, Ashley is pushing a box of Christmas decorations across an ice rink. She's doing so with a force of 25 newtons, and you can see what that force looks like in relation to the box below. It tells us that the box starts from rest, ends with a speed of 4.2 meters per second. We want to know how far did it go. And it also tells us to assume the ice is frictionless. What I would like you to do right now is to pause this video and attempt to solve for how far the box travels using the work-kinetic energy theorem. When you unpause the video, I will go through the process of solving for it, and you'll be able to see what the final answer is at the end. Okay, here's how we solve this problem. We know the net work is equal to the change in kinetic energy. And in this case, the only force doing work is the force that is applied. Just as before, if we were to draw a free body diagram, we would have normal force pointed upward. We would have the gravitational force pointed downward. And we'd have this applied force pointed in the direction that you see on the diagram here. Normal force and gravitational force are both perpendicular to the displacement, because this box would be moving to the right like so. And so they don't do any work. So the only work is the work done by the applied force. And that's equal to the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. We know that we can represent work done by a force by doing that force times the displacement times the cosine of theta. And we know that kinetic energy is 1/2 mv squared. So here I have 1/2 m v final squared minus 1/2 m v initial squared. Well, the problem tells me that it starts from rest. So I know v initial is 0, which means this whole term is equal to 0. Okay. If I'm trying to find delta x, then I'm going to divide both sides by applied force and cosine theta. And so I end up getting m v final squared divided by 2. That came from the 1/2. I just put that 2 in the denominator instead of putting the whole 1/2 in the numerator. Times applied force times cosine theta. So we're given many of these numbers. We're told that it's a 23 kilogram box and that its final velocity is 4.2 meters per second. Don't forget to square that. We're told that the applied force has a magnitude of 25 newtons. The thing we have to think the most about is what angle to plug in as theta. Is it 60 or is it some other angle? Well, the biggest thing to remember here is that theta is the angle between my displacement vector and my applied force when they're placed tail to tail, like you can see here. That angle is not actually 60 degrees, but instead that angle is 30 degrees. And I know that because this force vector makes an angle of 60 degrees with the vertical. So the cosine that I plug in here is 30 degrees. Then I just get to plug all that into my calculator to figure out how far this box was pushed. And I end up gathering that delta x is equal to 16.2 meters. Again, a reasonable distance to be pushing something across an ice rink. Hopefully after watching this video, the work-kinetic energy theorem makes a bit more sense to you, and you're able to apply it to problems on your own.